Subject: Physics, Simple Pendulum, Grade 10. Simple Pendulum. Good morning, dear students. Today, we are going to study a very interesting topic in oscillatory motion, the simple pendulum. You have all seen a pendulum in a clock, or maybe in science labs. It is just a small ball hanging with a string moving back and forth. But in physics, we study it as a model of simple harmonic motion. Definition: a simple pendulum is an idealized model. It consists of a point mass, bob, a light, inextensible string, fixed, frictionless support. This restoring force is what causes the motion. Dear students, by definition, a simple pendulum is made of a point mass called the bob, attached to a light, inextensible string, and suspended from a fixed support. The bob swings back and forth under the influence of gravity. Assumptions. For a real pendulum to behave like a simple pendulum, the bob is very small compared to the string length. The string's mass is negligible compared to the bob's mass. The string is perfectly straight and does not stretch. To make calculations simple, we assume some ideal conditions. For example, the bob is small compared to the string length. The string itself has no mass, and it does not stretch. In reality, these are approximations, but they work well. Given weight of bob, W equals mg. The bob is at an angle theta from the vertical. We resolve the weight mg into two perpendicular components. 1. Component along the string. This lies along the direction of tension. Using trigonometry, W equals mg cos theta. Why? Because this component is adjacent to the angle theta. This component is balanced by tension, T, in the string. T equals mg cos theta, for equilibrium along the string. 2. Component perpendicular to the string. This component pulls the bob toward the equilibrium position. Using trigonometry, W's and equals mg sine theta. Why? Because it is opposite to the angle theta. This is the restoring force. Frestoring equals mg sine theta. Finally, result, mg equals mg cos theta plus mg sine theta, where mg cos theta balanced by tension, mg sine theta restoring force causing motion. If you want, I can also derive the equation of motion. F equals ma equals minus mg sine theta, and show how it becomes simple harmonic motion for small angles. Now, students, let's see what happens when we pull the pendulum to one side and release it. Gravity acts downward with force. We resolve this weight into two parts. The component, colleague, which is balanced by the tension in the string. The component, colleague, which pulls the bob back to its original position. This force is called the restoring force because it always tries to bring the pendulum back. Restoring force. Here is a simple and clear explanation of the formula. Frest equals minus mg sine theta. 1 mg. This is the weight of the bob, mass times gravity. 2. Theta. This is the angle the string makes with the vertical when the pendulum is displaced. 3. Sine theta. This gives the component of the weight acting along the arc of the pendulum's path, tangent to the swing. 4. Negative sign. The minus sign means the force always acts towards the equilibrium position, the center, so it is a restoring force. When the pendulum bob is pulled to an angle theta, gravity pulls it straight downward with force mg. Only a component of this force pulls it back toward the center. That component is mg sine theta. But because it restores the bob back to the middle, opposite to displacement, we add a negative sign. So, if the bob is displaced to the right, plus theta, force is to the left, minus. If displaced to the left, minus theta, force is to the right, plus. If the bob moves to the right, the force pulls it left, and vice versa. That is why the force is negative. It always opposes motion. Small angle approximation. Sine theta equals Lx. In the pendulum diagram, L equals length of the string. X equals small horizontal displacement of the bob. Theta equals small angle made by the string. When the angle theta is small, the arc and the horizontal displacement are almost the same shape. So in the small right triangle, sine theta equals hypotenuse/opposite. Opposite side equals x. Hypotenuse equals L. Therefore, sine theta equals x/L. We use the word approximately because this is only true for small angles, less than about 10 degrees. Now students, if the angle is very small, we can use a mathematical approximation. Here is the horizontal displacement and is the length of the string. Equation of motion into restoring force. Frest equals minus mg/L into x. If you pull the pendulum a little to the side, a force pulls it back. The more you pull it, the stronger the force becomes. F equals ma. ma equals minus mg/L into x. Left side, ma. The mass times acceleration equals the force on the bob. Right side. Minus mg/L into x is the force that pulls the bob back to the center. The farther you pull the pendulum, x, the stronger it accelerates back toward the middle. By Newton's second law, force equals mass times acceleration. Substituting values, we get a equals minus g over L into x. This shows that the acceleration a of a pendulum is proportional to the displacement, x, and acts in the opposite direction. Here's a very simple explanation. A equals minus g par L into x. A equals how fast the pendulum speeds up or slows down. X equals how far the pendulum is from the middle. G par L equals a number that depends on gravity and string length. Minus equals shows the pendulum always goes back toward the middle. In short, the farther you pull it, the faster it wants to go back. So students, we conclude that a simple pendulum, when displaced by a small angle, performs simple harmonic motion. Its restoring force is proportional to displacement, and its motion is periodic and regular. Thanks for watching Forces School System YouTube channel. Like, comment, share, and subscribe. Stay healthy.